Hello everybody and welcome to the Count Submatrices with all ones coding question. We are given a binary matrix, mat, and we should return the number of each submatrices that have all ones. For this example, if this is our matrix, there are 24 submatrices full of ones. And there can be submatrices that only consist of one item, like this one, or this one, or this one, or this submatrix. This is another valid one, also this one, and so on and so forth. You got the idea. Let's start by using the first pillar of the bulletproof formula, which is coming up with a brute force approach. A brute force approach is a slow algorithm that tries out each and every possible contender to be a solution. So, our contenders for this problem are submatrices. So we should select every single submatrix and then check for the property. How can we select a submatrix? Well, we need to think about what every different submatrix is defined by. And there are exactly 4 numbers, and they are as follows. We have an upper row, which I'm going to denote as up row, then we have the left column, then we have the down row, and of course the right column. The up row and left column are basically the coordinates of the upper left corner of the submatrix. For example, if their values are 0 and 1, then the upper left corner will be on row 0, column number 1. So this is gonna be it. Then the down row right column are the coordinates of the lower right corner of the submatrix. So for example, if this is the upper left corner and down row is 2 and right column is 3, then the lower right corner is gonna be on row 2 and column 3, so it's gonna be this one. So this is the submatrix with this upper left corner in 0, 1 and this lower right corner in 2, 3. It's basically this one. By selecting every possible quadruplet of 4 numbers which have this meaning, we will basically select every single submatrix of our matrix mat. And in order to select every single quadruplet, we will need 4 nested loops, each one for each of these 4 items. Let's start with the first loop, which will select the up row. What values can the up row take? For this example, it can be 0 for the first row, it can be 1 or it can be 2 because the number of rows of mat is 3. So in the general case, up row, I'm gonna write a for loop and I'm gonna say that up row can be in the range starting at 0 and going all the way to the length of the matrix minus 1 because this argument is exclusive. Now let's think about the left column. For this example, it can be 0, the first column, or 1, 2 or 3 because there are 4 columns. So similarly, the left column can take any value in the range starting at 0 and going all the way to the length of mat of 0, the length of the first row, which is going to be the number of items in that row, which will be also the number of columns of our matrix. And this argument is exclusive, so this is okay. Now let's think about the down row. Technically, it can take all the values from 0 to the length of mat minus 1, exactly like up row, so I can copy paste this and say down row instead. And let me remove the spaces right here, but there is a catch. Because we said that up row is going to represent the upper row of the matrix and down row the lower row of the matrix, down row should always be greater than or equal to up row. Just think about it. Can you have a submatrix whose upper row is 2, for example, and down row or lower row is 0? Well, can you have a submatrix that starts here and ends above? No, you cannot. It doesn't make any sense. So, down row is gonna be any number in the range starting at up row and going all the way to the length of mat, the number of rows, minus 1. And similarly, right column can be any integer starting from left column because it has to be greater than or equal to that value. So I can copy paste this for loop right here. This is gonna be right column. This now is going to start at left column and the maximum value it can take is still the number of columns minus 1. So inside this 4 nested loops, now I have selected my submatrix and I'm gonna ask myself, is this submatrix full of ones? If so, I'm gonna increment the answer. So I'm gonna have something like mat count, a global variable, initialized at 0. If so, I'm going to increment it. And of course, in the end, after trying out every single submatrix, I'm gonna return the mat count. Very well. Now, there are a couple of ways to answer this question. Of course, you can do it in a brute force manner. You can loop over the whole submatrix. Maybe write a function in which you are going to have 2 nested loops to loop over all the items of that submatrix, and when you encounter a 0, you can return false and exit the function, and in the end return true. Or you can even answer this question in constant time using partial sums on a 2-dimensional array. You can pre-compute the partial or the prefix sums right here before selecting the submatrices, and then you can use the pre-computed prefix sums to compute the sum of this submatrix given by these 4 integers and basically check if the sum of that submatrix is equal to its area. The area is equal to the width times the height. The width is basically going to be the right column minus the left column plus 1, and the height is going to be the same formula but now for the rows. It will be the up row minus the down row plus 1. So for every single submatrix with these 4 coordinates, you will compute this sum using prefix sums in constant time. You will compare it to this product, and if it is equal, as I said, we are going to increment mat count by 1. And here is our first brute force approach. Now let's analyze its time complexity real quick. This for loop is going to make n iterations, where n is the number of rows, so let's write a big O of n right here. Then this for loop is going to make m iterations, where m is the number of columns, so big O of m right here. The third loop is going to make n minus up row plus 1 iterations, because we start from here, which is going to be at most big O of n, and also this one m minus left column plus 1, which is at most big O of m. And so the final time complexity will be big O of n squared times m squared. And the extra space, because we pre-compute the 2-dimensional prefix sums, so we will use an extra matrix, the extra space will be big O of n times m. Now we'll move to the next step, which is optimizing this brute force approach. This is quadratic time complexity because we have 4 nested loops, or if you suppose that n is equal to m, because they might be, this is something like n to the power of 4. We want to improve it to at least a cubic time complexity, which would be something like n cube, or if we use n and m as we should, either an n times m squared or n squared times m. We cannot have all these 4 loops, or in other words, we cannot select all the 4 coordinates faster than quadratic time. So what we will have to do is limit ourselves to selecting at most 3 of them. And let me give you a pro tip. Usually for coding questions that involve a matrix and submatrices, when the brute force approach involves selecting every single submatrix, in order to optimize it, we will select only the upper row and the lower row. So we will end up only with 2 nested for loops, more exactly this one and this one. So let me remove all of this code. We won't need it anymore. We will keep these 2 loops. Let me remove this, and also we can remove all of this.
Hey guys, Andy here. If you find this video valuable so far, don't forget to join our free Facebook group in which we teach you how to develop your problem solving skills and thinking process in order to ace the main coding interview. We show you how to get out of tutorial hell to not go to thousands of interviews in vain. And last but not least, how to develop your code literacy in order to write quality code that's readable and scalable. In this group, each week we will have a live call in which we answer any burning questions you have about the coding interview, or we hold a live coding interview simulation like this, or we talk about communication, problem solving, the MEG learning path in order to ace the interview, and a lot of valuable topics. So see you there. PS, all you have to do is click the link in my description, answer the questions, and I'll see you inside.
The upper row is still from 0 to the length -1, and the lower row is still from the upper row to the length -1. Now, inside these two nested loops, when we are right here on each iteration, instead of knowing all the 4 coordinates, we only know these 2, and now the columns are unknown. And what we are going to do is count how many submatrices with this upper row and this lower row are full of ones. And let me show you on this example to better understand what happens here. On the first iteration of this loop, up row will be assigned the value 0, so let's write this down, up row is 0. Then we enter this loop and down row will be assigned the value of up row, which is also 0. Then we enter this for loop and down row will be assigned the value of up row, which is 0, so down row will also be equal to 0. So right here at this iteration we are interested only in the submatrices between rows 0 and 0. You can imagine this like we slice this section between these two rows of the whole matrix, and we count how many submatrices are full of ones from this section. And as you can see, we have this one, we also have this one, and this is the one. So we are going to add their number, which is 3, to math count. Perfect. Then we move to the next iteration of this for loop where down row is going to get incremented. So let's write this down. Up row is going to still be 0, down row will become 1. And so we are interested in the submatrices that have the upper row 0 and the lower row 1. You can picture this as like we slice this section out of the whole matrix right here, and now we are left with this one, and we care how many submatrices are full of ones. But super importantly, we will only count submatrices from this section which have the upper row exactly this one, up row, and the lower row exactly this one, down row. We will not count submatrices like this one or this one at this step. They will be counted when up row and down row are both 1, so we choose only this section right here from the matrix. And also at this step we will not count submatrices like this one or this one. They were already counted when up row and down row were both 0. So the submatrices full of ones with upper row 0 and down row 1, which we will count at this step, are going to be this one, and this one. Which means that math count is going to get incremented by 3. Then we will move to the next iteration of this for loop. Down row is going to get incremented, so let's copy paste this, and down row is now 2. So we are interested in submatrices that have the upper row 0 and the lower row 2. It's like we slice this section out of the matrix and we look for submatrices full of ones. And we are going to find this one, and this one. Again, we're not gonna count submatrices like this one because their upper row is 2 and up row right here at this step is 0. We're not gonna count submatrices like this one or like this one, which was already counted before. And now this loop is complete. We will get back to the outer one and we will increment up row. So let's copy paste this, but now up row has value 1. Then we enter again this loop and start from the up row, which is value 1, so down row will be assigned value 1. And we are interested in the submatrices with upper and lower row both equal to 1. So submatrices from this section, let's take it right here, and we will find 1, 2, 3, 4, 5, and 6. So math count is going to get incremented by 6. Then we move to the next iteration. Down row is going to get incremented, so up row is still 1, down row is now 2, so we care about these submatrices from this section which have the upper row exactly this one and the lower row exactly this one. How many of them there are? 1, 2, 3 of them. So met count will again get incremented by 3. And now this loop, the inner one, finished. So we are going back to the outer one. We are incrementing up row. Up row will now have value 2. And down row will start at up row, which is 2. So this is going to be its first and only value. And we are interested in submatrices from this section, which are full of ones, and we have 1, 2, 3, 4, 5, 6. So met count, just like here, is gonna get incremented by 6. And then this loop, the inner one, finishes. We try to increment up row, but there are no more values in this range. So this one also finishes, and we should have our correct met count. Let's check. 3 plus 3 is 6, 9, 15, 18, 24, which is the correct answer. Okay, so I hope you really understood how this approach with only selecting the up and down rows works, and how it will lead us to the correct answer, because we are going to count every single solution submatrix exactly once. Now what's left to do is figure out for every single pair of up row and down row how to count how many submatrices like that are full of ones, and we still have a big O of n from here, a big O of n from here, so we have big O of n squared so far, which means that we can still come up with a big O of m algorithm to achieve this, and we will still have a faster solution than the brute force approach, which is great. Let's take one of the examples and show you how it's done. So, suppose up row is 0, down row is 1. As I said, we are basically selecting a section from our matrix. So if you take a look at this matrix, these are the rows, this is the selection that we've made. Now what we are going to do is turn this section, which is basically a submatrix, which is two-dimensional, into a one-dimensional array. And I'll show you exactly what I mean by that. Inside those loops, I'm going to create an array, full column, with the following definition. Full column of some column is going to be 1 if all the items in this column, so on column call, between the rows that we selected in our nested loops, so between rows up row and down row, if all of these items are ones. Let's take a look at this example. So this is our selection, and we can see this. On row 0, not both items are 1, so full column of 0 will be 0. On column 1, both items on both rows are 1, so this is going to be 1. Then this is also going to be 1, as both of these are 1s. And finally, full column of 3, on column number 3, not all the items between our rows that we selected are 1, one of them is a 0, so that's enough to say that this item will be 0. I am going to create this array, and now the original problem, which is counting submatrices between up row and down row, reduced itself to a problem involving only the full column array. And that problem is counting how many subarrays full of ones are in this array. For example, this is a subarray full of ones, which corresponds to a submatrix in our section that is also full of ones. Then this is another subarray that is full of ones, which corresponds to another valid submatrix full of ones from our section. And also we have this subarray which corresponds to a submatrix from our section that is full of ones. So the answer for the new problem right here is 3. There are 3 subarrays full of ones. So what we are going to do is increment met count by 3, because all of these 3 subarrays correspond to one submatrix that we are interested in. Let's take another example. Let's suppose up row is 0 and down row is 2, so we are basically selecting the whole matrix. This is how the section looks like. Let me unindent this. Perfect. And next we will create the full column array specific to this section. So let's see. Full column of 0. On column 0, are all the items between up row and down row equal to 1? No, they are not, so this is gonna be a 0. Then on column 1, are all the items on column 1 between those rows equal to 1? Yes, they are, so this is a 1. Then this is also going to be a 1, and this is going to be a 0. How many subarrays are there in this array that are full of 1s? 3 of them. It's this one, which corresponds to this valid submatrix full of 1s from our section. This one, which corresponds to this valid submatrix from our section, and also this one, which corresponds to this one. So we will find 3 subarrays, which means that there are 3 submatrices, so we should increment mat count by 3. If you think about it, what happens is that when we find a subarray full of 1s in our full column array, for example this one, which starts at index 1 and ends at index 2, this left and right endpoints are actually going to correspond to the left and right columns of the submatrix that we will count. So for this one, 1 and 2, this is the left column, this is the right column, and the up and down row are the ones from this current step, which is 0 and 2. So for every single pair of up row and down row that we select, by counting a subarray full of 1s in our full columns array, which we will see in a minute how to create it, we are basically counting a submatrix that is full of 1s and has the coordinates up row, 0 right here, down row, 2 right here, left endpoint right here as the left column, right endpoint right here as the right column. Very well, so I hope this is clear. Now let's find out how to create the full column array for every single pair inside these 2 nested loops. One way to do this is actually loop over the columns. So for each column in range starting at 0 going all the way to the length of matrix of 0 minus 1. And let me first create the full column array. So I'm gonna create an array which is initially going to have only values of 1 and a length of the number of columns. So inside this loop, full column of column is going to be initially 1, which is basically me assuming that all the items on that column between these 2 rows are equal to 1, and I can actually check for the opposite by looping over those items. So I know the column, now what I have to do is loop over the rows. For every single row between up row and down row, I'm gonna say +1 because I wanna have down row inclusive. What I can do is check if matrix of row and column is 0, so if not this item, alright, then I can set full column of column to be equal to 0 and I can break. So as I said, I'm supposing for each column that those items are 1, then I'm actually looping over them, and the first time the contrary is proven to me, I find an item equal to 0, then I'm gonna set the full column of column to 0 and I can break as I don't need to check anymore. Very well. Now of course the problem with computing the array in this way is that it is slow. If you think about it, how many columns will there be? There are m of them. So this is gonna be a big O of m, which is not a problem, but then we will loop over these rows. There are going to be down row minus up row plus 1 rows, which is gonna be at most n rows in the worst case. So this is gonna be big O of n. So now I have big O of n, inside a big O of m, inside big O of n, inside big O of n, and so I'm back to the previous time complexity. I haven't achieved anything. But that's not horrible. As you know me, I love brute force approaches because most of the time it's not that hard to optimize them if you have enough experience. We can optimize computing this array in a way that is similar to some optimizations we have made for the maximum sum subarray coding question from big O of n cubed to big O of n squared. If you can remember that, we basically used the fact that we already computed the sum of some subarray, and so when we moved to the next one, when we incremented that right endpoint, we only needed to add the new number to the sum instead of computing the sum from scratch. This is the same right here. If you think about it, for every single up row and down row, I'm computing the full column from scratch, initializing it, looping over the columns, and for each column, for each item of full column, I am looping over all the items on that column to check if there is one equal to 0. But maybe I shouldn't do this extra work. And let's actually take these examples, right? If up row is 0 and down row is 1, let's suppose for that step I have computed the full column array and it's this one. I know it. Isn't there any way to use this array, or more exactly update it for the next step when down row gets incremented and we basically add a new row to our section? Yes, it is. Check this out. If at this step full column of 0 was 0, this means that at least one of these two items is a 0. And so, on the next step, when up row will have the same value and down row will just get incremented, so I have a new line, I will basically have a new element into this column 0. So if at least one item from these two was 0, if I add another one, it doesn't matter if it's a 0 or a 1 like here, there will still be an item on this column which is equal to 0. So this item will still be 0 as it was in the previous step. Same if you take a look at full column of 3. It was 0 at this step, so there is at least one item on this column which is equal to 0, which means that on the next step, I'm just gonna add a new item to that column. So it doesn't matter whether it's a 0 like here or it can be a 1, there will still be an item which is equal to 0 on that column. So if this was a 0 on the previous step, it will stay a 0 also in the next step. Only the values of 1 from this array are the ones that might change. Check this out. At this step, this item was a 1, which means that all the items, both of them in our case, were 1s on this column. So when we move to the next step, we basically add a new item to this column. This new item can be a 1, which means that all the items on this column are still going to be 1s, so this is still going to remain 1 as it was in the previous step. But if this new item was a 0, then, even if this item was a 1, all these items were 1s. Now, because I have a new 0 in this column, it's enough to say that this item will become a 0. And it's the same for column number 2. This was a 1 on the previous step because both of these were 1s. Now I'm gonna have a new item. If it's a 1, perfect, then this item will keep its value of 1. But if this one is a 0 now, then this one will also become a 0. So what I'm going to do instead is I'll take this full column from here and I will create it right here for every new value of up row, because when we move to the new up row, we'll have to reset the full column, right? It doesn't matter if the full column was full of zeros at this point. On the next iteration, when up row becomes 1, we have a new upper row, so we will start a brand new section instead of adding new rows to the previous ones. So we should also reset the full column. Alright, let's do it here. Then we will loop over the down row, and inside this loop we will basically add a new row to our section. So we will use the previous full column array, but we will update it where it's necessary. So I'm still looping over the items of full column, which are the columns of the matrix. And for each of them, instead of looping through all the items on that column, because I know the answer for most of them besides or except this new one that came with the new down row, I'm just going to check that. So check this out. I'm going to remove this for loop. Let me unindent this code. Perfect. I'm not gonna need this break. Okay. And now I'm just gonna check for matrix of down row and this column. If this is a 0, now the full column will be a 0. So if in the previous case this full column of 0 was a 0, then it doesn't matter if we enter or not this if statement, it will stay a 0. But if it was a 1 and this new item is a 0, then I will make it a 0, which is perfect. And that's about it. Now, as you can see, we have this big O of n from this for loop. Now, creating the full column is of course going to be big O of m, as we have m items equal to 1 initially. But this big O of m is not nested inside this for loop, so big O of m will not get multiplied by this big O of n. They are separate. What we'll actually have is the big O of n times, parentheses, this big O of m first, then after this is finished, we are going to enter the for loop, which is this big O of n, and then inside this for loop, we have this big O of m, so these two are going to get multiplied. This is going to be a big O of n times m, and now if I rewrite all of this, I'm gonna have big O of n times big O of m, perfect, then plus big O of n, which was the common factor, times big O of n times m, so I'm gonna have big O of n squared times m from there. So it's a big O of n times m plus n squared times m. This is the greatest one, but it's still better, faster than the previous brute force, so I'm happy. Now I know the full column array for every single pair of rows that I select. And now the final piece of the puzzle, let me remove this code, is counting how many subarrays full of ones are within this binary array full column. And this shouldn't be new to you, we solved lots of similar coding questions in the arrays chapter in the beginning of the course. Basically what we'll do is loop over the full column array, and I can do that using values, so for each column in full column, and I will have an extra variable. I'm gonna call it current length, which is going to represent the length of the subarray full of ones that ends in this current item, which is call. So I'll have my cases. The first one is if call is 1, then the current length will get incremented by 1. Otherwise, if column is 0, then the current length will get, of course, reset to 0. Now for every single item, if I know the current length, I know that there will be exactly current length subarrays full of ones that end with that item. For example, right here, the current length of this item is going to be 2, so I'm gonna add 2 to the solution because I wanna count this one and also this one which ends in the same item. So what I want to say after updating the current length is mat count, which is actually my global solution, gets incremented by current length, and this is great. Now in the end I should return mat count, so let's do that. Now let's analyze the time and space complexity. We kinda did that, we were super close. I basically analyzed it up to this point and I came up with this, okay, but we can do it again real quick. So this is going to be a big O of n, the main for loop where everything happens. So everything will be multiplied by this big O of n. Then inside, as I said, first we have this big O of m. I'm just going to write m down. Then separately, so plus, I'm going to have this n. Inside this n, I have this for loop, which makes m iterations, so they will be multiplied. Then this is constant, alright. Then I do this, which is constant, and then I'm looping over the full column array, which is big O of m, because I have m items, one for every column. So check this out. I'm gonna have another m, but be careful, this m is separate than this m right here, but it's still inside the n right here. So this n will multiply by m, the first one, plus m, the second one, okay. Now let's see, this is constant, okay. So this is big O of m in total, this piece of code, plus this big O of m, therefore this one, which is 2 times m, which in terms of time complexity is still big O of m, right? Then times the n from right here, which is going to be added to this m right here, and both of these are going to be multiplied by big O of n, so still n times m plus n squared times m, and the greatest one is the n squared times m, so this is going to be our final time complexity. And the extra space used, let's check this out, because it's going to be also less than the one used in the brute force approach with the prefix sums. That one was big O of n times m, but now let's see what we use. We use the full column array, which has a length of m, so we have m extra space from here, and then I don't see any extra array. I only see loop variables and other variables which are constants. So we have a big O of m extra space. Well, this is not 100% technically correct, because we create the full column array every time we enter this for loop. So for every single iteration, right here, there are n of them, we create a new full column array of length m. So technically we will have n different full column arrays of length m, and so we will have n times m extra space. This is actually a conversation about the garbage collector, which I'm not familiar with in Python, but what I can tell you is that in many programming languages, there is a garbage collector which realizes when you're not using anymore some memory, some space that you've created, and so it will release that memory that you're not using anymore, or as its name suggests, it will collect the garbage, and so in our case, check this out. It's gonna figure out that, okay, for up row initially 0, you're creating this array, then you do all this stuff, doesn't matter, and then for the next iteration when up row is 1, now you're creating a new array and you assign it to the same reference full column. So if you only use full column in your algorithm, it's clearly that on this current iteration you are only using the new created array, and the old one is not going to be used anymore. So with the garbage collector, you can Google it for Python, I think it's an interesting topic. If it realizes that that's not used anymore, it will release it for you, and so you will only have one array existing in the memory, which will lead to a big O of m extra space used by our algorithm. Whether if that's the case or not, our job as great developers is still to figure this type of problems out and fix them when it's possible. And so the question is, do we really need to create a new array in memory for every value of up row? And the answer is no. We only do this line of code in order to initialize the full column array with values of 1 for every single up row. But we don't need to create another one. We can definitely use the same one. So what I can do instead is actually have this list to be global right here, and then I just need to initialize it with values of 1, so I can loop over those items, but not using values. I need to loop over indices, because this variable call would just be a copy of that item, right? So if I say call equals 1, the actual item in full call will not change, only this variable which is not referencing it. So when I loop over items, I know that I'm gonna directly work with the items directly with their references. So I can say full column of I is 1, and this is gonna work. I know it's a little bit ugly. Maybe there exists a method, I've googled it and I haven't found any, like fill or something to do this better, but list comprehension or something like that is not going to work, because you can do full column equals 1 for I in range, and you can say length of mat of 0, right? But guess what? This is still going to create a new list in memory, which is gonna be empty, and then for every iteration right here is gonna append the 1. But the list, as I said, is still a new one in memory. What you have to do in order to work with the previous and the same one is loop over it with indices and set them equal to 1. So yeah, this should also work. Let's check it out. I still have a 13, all good.